Key properties of the system. We already talked about this. What are key properties of the system? So, entropy and temperature are key properties of the system. Pressure and volume are key properties of the system. Chemical potential and number of particles, if you're a chemist, are key properties of the system. Now, if you look here, I coupled entropy with temperature and pressure with volume and chemical potential with number of particles. If you remember the last diagram where we considered the work by or work on the system, area under the curve, I plotted P versus V. In this course, we're mainly going to be dealing with related to this, T S diagrams and P V diagrams. I have areas under both. This area represents work on and by the system. This area represents also work done on or by the system, but usually we talk about the area under this curve is net heat transfer, the area under this curve is net work. If I do my mu versus n curve and I'm a chemist, then I'm talking about the work associated with a reaction, which is important. We're not going to deal with chemical potential. I'm just showing that you can take. So if I look at this, you'll learn more about the reason these are coupled in this way. But now I just, for the meantime, they're written like this. I just want you to consider that I have TS, which is an intensive, extensive couple. And I have PV, which is the same. And likewise, I have mu n. So I coupled things in a way, so I'm coupling an intensive property with an extensive property, an intensive property with an extensive property, and I'm doing it, and when I do that, I make that type of a marriage. Then when I do plots like shown above with this TS and PV diagram, there's some real fruitful meaning, and that's coupled with areas under the curves, right? So you get to apply your calculus to get things with meaning. I have a system, and coupled right next to it is a subsystem, and out here I have surroundings. I wanted to see what time it was. So I have my system 1, I have my system 2, and I can draw a boundary around system 2. I can draw a boundary around system 1. And I can draw a boundary around my combined system. And of course, given I have my systems, I can say that there's an internal energy of system 1 and there's an entropy of system 1. I can say that there's an internal energy of system 2 and an entropy of system 2. Is internal energy that can be considered an equation of state? Okay, yes. So what do I need to define the equation, a state of a system? Two independent. So of course there's temperature and pressure. I know the temperature and pressure of my system 1. So therefore, based off of the first and second law of thermodynamics, I know the internal energy and the entropy. Now, internal energy plus internal energy. So if I know the internal energy is system 2 and I know the internal energy is system 1, and then I want to can I add them? Is this true? Someone said no. Is that, can I add the internal energy this, the internal energy this to say the internal energy of both? If I draw a boundary, I have an internal energy of both. This works. Now let's do entropy. Entropy of system 1 plus the entropy of system 2 equals the entropy total. Let's draw a little water molecule here. And there's some degrees of freedom associated with it. And then I only have one molecule here with the degrees of freedom. It turns out that entropies are additive, just like internal energies are additive.
When you add the second one, you're giving it more options, right?
Well, I wanted to do that, but I probably shouldn't have did that. Entropies are additive. So, in this case, system 2 is much smaller than system 1. And in this case, system 1 can be a heat reservoir. So when I say that, I'm going to say that there's heat that can be transferred between system 1 and system 2. Because system 2 is much smaller. And so if I take an ice cube, well, let's not take an ice cube. Let's not consider a phase change. If I take a penny at 1,000 degrees C, well, let's not do that high because it would melt. At 400 degrees C, it's not going to melt yet. I take a penny and I drop it in the ocean. Do I change the temperature of the ocean? So you can kind of see. Now, if I take an asteroid and put it in the ocean, right, I'm going to change the temperature of the ocean. But you can kind of see that the system size dictates whether something can be a heat reservoir or not. So the ocean cools the penny. The penny changes, but the ocean doesn't. So you need something, a system much smaller. Usually we say something like thermal mass. The total mass of the system is coupled that. So we can talk about this idea of a thermal reservoir. So now related to this entropy being additive, let's write out the second law. So I have delta S is equal to the integral of Q reversible over T. So I can have some heat exchange. Okay? Now, let's say system 2 doesn't have any mass coming in and out. Yes?
With your penny in the ocean example, what happens to the energy from the penny?
Well, it goes to the ocean. Or,
The ocean doesn't heat up?
well, I mean, it does, but at such a small value that it doesn't look like it from a thermodynamics perspective.
Okay,
So if I were to, there's no way I could measure the increase in the change in temperature of the whole ocean by putting a penny in it.
so technically that's an approximation.
Yeah, it's approximation, but really, it doesn't heat up. So we have to define a reservoir, whether it's a mass reservoir. So if I go to the treasury, and I take a penny out of the treasury, does the treasury lose mass? Yes, technically, but does it really notice it? No, because it's such a small amount of mass that's being. Maybe they would because they're the treasury, but you get the general idea that we have to define a reservoir, and all we're saying is for some fluctuations in a smaller system, it doesn't influence the properties of the reservoir.
Your round-off error is going to be larger than
Wow.
what the change is.
Well, probably my ignorance is larger than all of it. So there's changes in entropy in my system when I add heat or mass or whatnot. And then I can look at the change in entropy of my system due to heat transfer in these different forms.
I have a question.
Yes?
Before we move on, at what point do you, if let's say that system 1 is just a little bit bigger than system 2, at what point are you going to you get what I'm saying? Like when, I'm having a hard time explaining. At
Yeah,
what
how do you know? How do you know when you can consider it a
exactly.
reservoir?
Like, when is system 2, when is the temperature going to be affected? At what point? Like how big is system? When do you or system 1? Assuming.
Yeah, so that's a good question, but you know, a lot of times in science we talk about orders of magnitude. So order of magnitude is a factor of 10.
Okay.
So you should have, you know, large orders of magnitude differences in masses of the system.
Okay.
Or different, you know, so I can look at the internal energy, you know, so I can do like a thermal energy of the system, a total thermal energy of the system. So if I have a volcano, you know, it's at high temperature, so there's a lot of KBT, there's a lot of thermal energy associated with it. So I could still have like a semi or something like that, but you know, but the volcano's at such a high temperature, there's so much energy there. So it's coupled to both mass and kind of a thermal energy. But you know, it's this gray area, so really you have to see, can I change the temperature pressure of my reservoir?
So it's a judgment call.
Yeah, but it's a judgment call, but you'd have to go through analysis, right? You'd have to define what is your level of acceptance. Is it is 1% change in temperature pressure good enough to consider my system a reservoir? Most cases I would say yes. In some scenarios 1% isn't good enough. In some cases 10% might be good enough. It's all based on the engineering. In general, we should say that it's a percent of a percent of a percent change in the properties of my reservoir for it to be considered a reservoir.
So it's just based on what you define it to be.
Yeah, because the reservoir, like what was just mentioned, it's just an idea. It really, if I drop a penny of 400 degrees C in the ocean, I do change the temperature of the ocean. So it's an idea. So then we've invented the idea of a reservoir to describe thermodynamics. Probably it isn't the best way to do thermodynamics because we had to make that approximation. What's that?
Is this something we're going to run into on an exam or we're going to have to make a
No, you'll have to make a judgment. Probably not. I want to do this one real quick. So we have the second law, and then I can rewrite it in this form. So so sometimes you can ask the question, what is the second law? And then I remember hearing, that is a tedious question. And I didn't like it, but now I like it. So, what is the second law? That is a tedious question. So if you don't remember this form and you don't remember that, maybe you can remember, I didn't like the second law, it was a tedious question. Oh yeah, that's right. So I can write it like that. And then maybe you can get the integral forms later on. But, okay, so tedious question. Okay, so entropies are additive. And then another ramification of the second law is energy transfers from high temperature to low temperature, and that's because of the second law, and that's because delta S has to be greater than or equal to 0. So a natural process wants to increase entropy. So if I just have hot system A, cold system B, I put them in contact with each other, I don't do anything more, I just let nature take its course. Heat goes from high temperature to low temperature in order to not violate the second law of thermodynamics that says that entropy should increase. The change in entropy should be greater than or equal to 0 for an isolated system. So in that case, I have system A and I have system B, and then I draw, in order for it to be isolated, I have to draw a boundary around it, like such. And so for in system A and system B, I have a temperature A, and I have a temperature B, and I'm going to say that TA is greater than TB, and this is some fictitious boundary, and given it's isolated, I really don't know what's happening inside, but I make isolated boundary conditions so no heat or mass can go in or out, no forms of energy, isolated. Now this boundary spontaneously breaks, and now I can have heat transfer between A and B. The only way for the entropy to increase or stay the same for this isolated process is for heat to go from high temperature to low temperature. Okay, I'll let you guys think about that. It's not, that's more like final type questions. Okay, so there's a few other things.
Before you go on, the area under the entropy temperature graph, what was that?
Okay.
You told us, but I didn't.
Yeah, I just said this is related to heat. So in this one, so this one is related to heat, and then I can do another thing. And so if I have clockwise, which is 2 letters in, so it's Q net in. And if it's counterclockwise, there's 3 letters out, so it's heat net out. I have another approach for that, but if I have a cycle, then the net heat in is equal to net heat work in or work out. But anyways, I wanted to really focus on the idea that intensive, and I just showed an example of a PV diagram where I couple an intensive with an extensive property, and then the area under the curve in that type of diagram has some very fruitful meaning. Yes?
Before you mentioned that entropy was additive, but what you just said with the isolated system sounds like it's otherwise if you put the two together.
No, I was talking about the temperature.
Oh, okay.
This has an entropy, this has an entropy. Okay? This has a temperature, this has a temperature, this has a pressure, this has a pressure. I have a spontaneous boundary here. There's an entropy of A. There's an entropy of B. If I say that this is basically just a fictitious boundary where I don't let anything transfer for some snapshot in time, then entropy of A plus entropy equals the total entropy inside. But I can separate them. So given this is at higher temperature, I'm going to say it's at higher entropy. And it's given that the TB is at lower temperature, it's going to be at lower entropy. How can I say that? Well, I can just go back to the third law of thermodynamics. Of course, that was in complete thermal equilibrium, but as I bring the system temperature to absolute zero, the temperature goes to zero. So in general, I increase the temperature, the entropy goes up. So this has higher entropy than this one. But I can add them. I get a total entropy of everything inside. It's additive. Now, when this boundary is spontaneously moved and I'm allowed to have heat transfer, or say the boundary it goes from, I have another isolated boundary here, and I make it suddenly open. A closed boundary condition, so only heat can transfer. Or take 2 copper blocks, and suddenly I put them in contact. I guess that's a better way of thinking about it. So I have 2 copper blocks, copper block A, copper block B. They're both at different temperatures. Right at some point, they're so close to each other that there's no heat transfer to be. And then spontaneously, they connect each other, and they're all within an isolated system. So the surroundings can't talk to A and B in any way, not even through photons. Then, I know that heat goes from A to B to satisfy the second law. The second law says that for an isolated system, I have this, where delta S has to be greater than or equal to 0. So I made this isolated, and now I want to know the direction of heat transfer based off the second law. And when I do that, A goes to B. So my total entropy of my system, S, equals SA plus SB, right? At state 1. I want to know delta S, which equals S2 minus S1, which equals SA2 plus SB2 minus SA1 plus SB1. Okay? I made this isolated. So I can say that at some final state, that A and B are at the same temperature. If I know they're at the same temperature, and I say that the A and B have the same mass, right, and they're made up of the same copper blocks, then I know that A and B have the same entropy. So A and B are the same in the final state. They're different here. I know that this value has to be greater than or equal to 0. Well, given I made it isolated, this all equals Q reversible over T. So S2 has to be greater than S1. I have a given amount of heat transfer. So I know that heat has to go from hot to cold. Second law dictates the direction of heat flow to satisfy delta S greater than or equal to 0. There's just two, we're going to talk more about this stuff later on. I want to do a quick review on properties of the system. So density, mass over volume, okay? Very familiar with. What we end up using a lot is this specific volume, which is V, which is 1 over density. But you can think of it as the specific volume, or I have it here. The specific volume is volume per unit mass. It's volume divided by mass. Now I drew these P V diagrams. What we like to do is P versus small v. And then coupled with the TS, I drew T and big S, but we really could do T and small s. So we like to break down some of these extensive properties in a per unit mass basis. You dimensionalize things. So in science and engineering, we commonly normalize or mess around with our equations by dividing by volume or mass or density. So a lot of times we take energy, but we could do an energy per unit density. We can do all these different things. Energy per unit mass, energy per unit volume. So a lot of times we take an equation and then we want to remove out, we say it's a constant density process, so we just divide the density by everything or whatever it might be. So a lot of times you do this in computer simulations. It's useful. So we do this a lot. PV to PV. TS, S1, S2, right? We go from these states, and we like to divide some of the extensive properties by mass or volume. I can't make a small p, pressure per unit mass. I can't do that. I can't say a temperature per unit mass. But I can say a volume per unit mass, specific volume. I can say an entropy per unit mass. So S, small s is equal to big S over m, and small s has units of joules per Kelvin per kilogram, whereas big S is joules per Kelvin. And so this has units of meters cubed per kilogram, meters cubed, kilopascal, Kelvin, whatnot. Also can look at pressure. Pressure, kilopascal, Pascal, Newton per meter squared. I can also couple it with, I can describe pressure, you know, in terms of atmospheres and bars or kilopascals or PSI or, you know, millimeters of mercury. But in general, it's just force per unit area. And so I have some conversions here. And then we could talk about gauge pressure, absolute pressure. But we, you know, related to what I was talking about per unit mass, you can see that we have absolute pressure and gauge pressure. But we don't see any small p's. We don't see a pressure defined per unit volume or a pressure defined per unit mass. Instead, we can just play around with absolute and gauge pressure. So gauge pressure is what you fill up your tires with 30 to 60 psi in your bike or car. So that's a gauge pressure. It's the pressure inside minus the atmospheric pressure. Example, car tires. And then here let's consider, now actually this is important now. So now they want to produce hydrogen, and it turns out they can devise things that are more efficient at producing hydrogen from water at really high pressures, but then when you put hydrogen at really high pressures, things get explosive. So let's just put a reactor at the bottom, at really deep in the ocean, so then I can use this pressure is the atmospheric pressure plus my rho GH, and then I ask the question, what is the required H for this pressure for a specific ration to be 100 atmospheres, and so I can just go through it. And so if hydrogen production, these devices, which is close to this 100 atmospheres, so these hydrogen producing devices, so we have hydrogen based cars, well you can kind of see, to produce that you need really high pressures to do it efficiently. So how far down do we need to put our reactor in the ocean in order to have a hydrogen production system? And if this is where we get a maximum efficiency, then we have to bring it down to close to 1,000 meters. But I'm just talking about pressure and height and things like that. I think we have 5 minutes. So why don't students ask a few more questions? Yes?
In the first law, you talked about adiabatic. Is that what we're saying, right? Adiabatic systems?
Yeah.
We've never built anything that works for, right? Like, we've never made a machine that's adiabatic.
Oh, there's a lot of things that are adiabatic.
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 Okay. Where only work comes out and there's no friction, there's no heat.
Yeah, so
What's an example of that?
I'm wondering. Okay, so the question was related to adiabatic systems and whether we've really dealt with something like that. And so if I just want to, I think this is good to go over. So energy in minus energy out equals the change in internal energy in my system. So this is the full energy balance. And in the first law of thermodynamics, right, the way I asked you, and I said, for an adiabatic process, the change in internal energy is equal to the work done on the system. So let's just write all this out. And so I have heat in plus work in plus energy associated with mass in minus heat out plus work out plus energy associated with mass out equals the change in internal energy in my system. And so if I have an adiabatic process, Q is equal to 0. So in this context, which implies Q in minus Q out equals 0, which implies that Q in equals Q out. I can have heat in and I can have heat out, it's just they're balanced by each other. So when I do this, I need to have, it said that for an adiabatic process, Q is equal to 0 implies the change in internal energy is equal to the work on the system, which means it's work in. So if I just cross these out to get it to this form,
Can you pull down a little bit?
thank you. So if I want to get towards what I said in words to this form, adiabatic process, the change in internal energy is equal to the work on the system. Then to get it into this equation, into this form, I need to cross out this, right, equal to this. And then I don't need to cross out these to get here. Well, I do, but I mean, these can cancel each other. So I just end up with work in equals the change in internal energy, which is the work on the system. Another student has a question.
Yes. Let's say that we're considering a piston system.
Okay.
Let's say that we draw a boundary just around the piston itself.
Okay.
Okay. When we're doing our energy balancing there being a work in because the piston, let's say, is being pushed down, in this particular scenario, it's being pushed down. Now, of course, in when we do thermodynamic analysis on gases, we of course do W equals interval E.
Mm-hmm.
But this is a rigid body being displaced. Do we consider the work in?
So you're saying to take this whole thing, what I have drawn here, and not to change the volume, but just to move it? Work? Or are you saying to move the piston actually down?
You have a boundary just around the piston.
Okay, so I'll draw a boundary just around the piston, not the gas. There's my boundary. I guess I could put it up a little bit to cover the shaft too, but
So this thing has work being applied to it to push it down. Right?
yeah.
When you do your energy balance, you're going to have.
Yeah, so let's say this is state 1, and I know that it has a velocity. A snapshot, it's being compressed, it has a velocity, state 1. And then sometime later at state 2, it looks like this. This is state 2. I did work on the system to compress the gas. So if I do this, V1 is greater than V2. Now if I compress the gas, really I probably did it, so P1 is less than P2. Now the work on the system is equal to the integral of P dV, and the work by is equal to the positive integral of P dV. But I did work on the system, so I decreased its volume. The pressure might have went up. If I just said if I compressed the volume at constant pressure, so only the temperature went up, right? Not the pressure. So if I did this and I said it was a constant pressure process, then I'd say if I wanted to know the work on from going to state 1 to state 2, and I said that the pressure didn't change from going to state 1 to state 2, all I did is increase the temperature and decrease the volume. So I could take the pressure outside, and then I would have the integral of V and with minus sign. And so the pressure didn't change, so then this ends up being what? V1, and so then I just get minus P V2 minus V1. Well, V2 is greater than V1, or is less than V1. So what does this end up being? This just ends up being P V1 minus V2.
This is when you have constant pressure, so just bring.
Yeah, but I mean I could put pressure in here. It'd still be the same thing. It's just I wouldn't be able to have a nice... I could still increase the pressure. It would still end up being work on the system.